So for the first one that we talked about was the Bode plot, right? So in Bode plot, what is happening is that, so we have two different plots. So two different plots as in, so we have a magnitude plot. So log the magnitude of the given transfer function, that is in dB in the y-axis, and in the x-axis we plot it with respect to omega, that is the frequency. And the second plot which is there in the Bode diagram, that is the phase plot. Okay, so the phase plot is basically if you have a transfer function of, let's say, g of j omega, then the angle or the phase angle of g of j omega, that is basically plotted in the phase plot. Separate plots. Okay, so you have to find out, you have to draw two separate plots. Okay, so polar plot you can say that it's sort of an extension of Bode plot, wherein what you can do is that you can combine the information about both the magnitude as well as the phase of a given transfer function, and you plot it in a complex plane. Okay, so what we do is that we have the sinusoidal transfer function which is given by, let's say, g of j omega. Okay, and this transfer function, so the magnitude of this transfer function is given by mod of g of j omega, and the phase angle is angle of g of j omega, right? So this we plot it in a polar coordinate axis or in a polar coordinate plane, wherein we change the value of omega from 0 to infinity. So you can write that this transfer function, this g of j omega, obviously this is a sinusoidal transfer function. Okay, so you can express this g of j omega in terms of real component plus j multiplied by some imaginary part. Okay, so this is how we would like to express the value of g of j omega in order to plot the polar plot. Okay. So basically what happens is that since we are varying the value of omega from 0 to infinity, so that means the polar plot will start at omega equals to 0 and it will end at omega equals to infinity. So what we'll do is that for a given transfer function or a given open loop transfer function, we'll first express it in terms of x plus jy, let's say. And from there, we have to, first of all, we have to figure out what is the omega equals to 0 point or what is the starting point of the polar plot. Correspondingly, we have to find out what is the ending point of the polar plot. Okay. So once we have found out the starting and the ending point, then so the starting point can be calculated by calculating the magnitude and phase of gh of j omega at omega equals to 0, and the ending point can be calculated at omega equals to infinity. And you can imagine, so this is, let's say, this is a standard or just a representative polar plot. So here you see that this polar plot is basically intersecting the real axis at some value. Let's say this is some value omega dashed. Okay, so this value, this omega dash, that can be found out if you equate the imaginary component of this g of j omega to 0. Okay, so in order to find out the place or the value of omega at which the polar plot intersects the real axis, you have to equate the imaginary part equals to 0, and from there you can find out what will be the value of omega at this point. And once you know the value of omega at this point, you can find out what will be the real value. So you can simply put that value in the real part, and this the actual real the real part of the given transfer function at this omega dash, that can be found out. Okay. Similarly, if this curve was to, in this curve actually it is not intersecting the imaginary axis, but let's say you have the transfer function is given in such a way that it intersects the imaginary axis. So in that case, that means that it is the polar plot is intersecting the imaginary axis, means that the real component is equals to 0. So similarly, if you just equate real part of g of j omega is equals to 0, you can find out what is the value of the frequency at which this polar plot will intersect the imaginary axis. And then you can find out what is the value of that at that position, what is the value of this imaginary component. Okay, so once you can figure out, so these four are the basic points which you need to find out while drawing a polar plot. Once you have found out these 4 points, then the next thing what you need to do is that either you can draw an approximate curve just by joining joining these points, or in order to draw it more clearly or to draw it more accurately, you have to consider other values between between, let's say, 0 to this omega dash, you have to consider one value, let's say omega 3. Then between omega dash and infinity, you have to consider, let's say, 2 or 3 more values, so that you can get a better approximated polar plot. Okay, so now let's try to do an example, then I think it would be more clear to you. So let's say that you have to draw the polar plot of an open loop transfer function, which is given by this. Okay, so you can simply write it as g of j omega, h of j omega. So you have to just substitute the value of s with j omega. So this will give you 100 by j omega whole square plus 10 j omega plus 100. Okay, so this is nothing but 100 by 100 minus omega square plus j into 10 omega. Now what we need to do is that we have to separate it out in, or we have to express this in terms of real part plus j into the imaginary part. Okay, so that means if you want to simply rationalize this one, so it will become 100 multiplied by 100 minus omega square whole square minus 10 omega, and the denominator will be 100 minus omega square whole square plus 100 omega square, right? So from here you can write it that the real part is 100 into 100 minus omega square whole square divided by this denominator minus j into 1000 omega by right. So this is how you have expressed. Also you have to find out, or in the other terms you can express this gh of, so g of j omega, h of j omega. So if you want to find the angle of this g of h, so this would be nothing but the angle of this transfer function. Okay, so the angle of the numerator is equals to 0 because it doesn't have any imaginary component, and so the angle will be minus tan inverse of 10 omega by 100 minus omega square. Now this angle is basically important because once we are plotting the polar plot, we need to find out that, suppose, so this is how the, so this is the real axis, this is the imaginary axis, right? So that means if, so this angle will be equals to plus 90 degree, then this angle is equals to plus 180 degree. Similarly, if you go to the in a clockwise direction, this will be minus 90 degree, and this angle will be minus 180 degree, right? So depending on what is the angle of this polar plot at different values of omega, you can specifically find out what are, which points in this complex plane they lie on the polar plot. So the first thing to do here is that you have to find out what is the value at omega equals to 0, what is the real component. Okay, so you see at omega equals to 0, the real part is equals to 0. Sorry, the real part is equals to 1, right? And the imaginary part is equals to 0, right? Similarly, at omega equals to infinity, the real part is equals to 0 and the imaginary part is also equals to 0. And if you find the angle of g of this open loop transfer function at omega equals to 0, so this angle of, I'm just writing g of h, so this is 0 degree at omega equals to 0, and the angle gh is equals to minus 180 degree at omega equals to infinity. So if you want to draw the polar plot, so let's say that, so this is the imaginary axis and this is the real axis. Okay, so at omega equals to 0, we saw that the, so it is, so this is the point 1, 0. So this would be the starting point. This is omega equals to 0. The real part is 1 and the imaginary part is 0. And at omega equals to infinity will be the point at origin. So this will be at omega equals to infinity, right? Because both the imaginary and the real parts are 0 at omega equals to infinity. Now next what we need to find out is that we have to find out whether this curve, this polar plot, that will intersect the real axis or imaginary axis or both. Okay, so let's say that we want to find out at what point this polar plot will intersect the imaginary axis. Okay, so intersection with imaginary axis means the real component should be equals to 0, right? So the real component is given by this part. So this would be equals to 0 means effectively you can write 100 minus omega square is equals to 0. So this implies that 100 minus omega square is equals to 0. So that means omega is equals to plus 10 radian per second, right? And at this, so at omega equals to 10, the value or the real component is obviously is equals to 0 and the imaginary part would be equals to, so you have to simply substitute the value of 10 in this part and you will get that the value of this imaginary part is equals to minus 1. So you can say that, let's say the polar plot will intersect. So if this point is 0, minus 1, so this would be at omega equals to 10. So it will start over here. At omega equals to 10, it will come over here, and omega equals to infinity, it will come over here. But this can follow any number of paths, right? So it can. So what we would like to do is that we would like to find out. So let's say between 0 and 10, we find out where this at omega equals to 5, which is the point corresponding to the polar plot. Okay. And similarly, so at omega equals to 5, if you simply substitute, so you see that the real part is equals to 0.9 and the imaginary part equals to minus 0.6. Okay, so that means it would lie somewhere over, let's say here. So this would be at omega equals to 5. So you can start drawing. So it will come like this. So we will make a smooth curve and we will join. Okay, so after this, let's say we find out at omega equals to 20, between 10 and infinity. So at omega equals to 20, the real part is approximately equals to minus 0.2. and the imaginary part is equals to minus 0.2, right? So that means minus 0.2, let's say over here, and so this point would be somewhere over here. So this is omega equals to 20. Okay. So from here, what it will do is that it will come over here, and then slowly it will go towards the origin. Okay. And here you see that since if you remember that, see here that at omega equals to infinity, the phase angle was minus 180 degree, right? So minus 180 degree means this part. So that means, so the polar plot, what it will do is that it will follow this minus 180 degree axis and it will enter or it will end at omega equals to infinity. So that means it will, why this phase angle is important? Because we can reach this origin via different paths, right? So I can have a phase plot which, so it can, this plot can come down like this also. In this way also it can reach this origin. It can reach origin by this way also. So there can be different ways of reaching the origin. So that's why we need to know, or we need to understand or find out what is the value of this angle of GH of omega at omega equals to infinity, so that we know that which asymptote it will, or which angle asymptote it would follow, the polar plot would follow in order to reach the terminal point. So that means here it has to follow minus 180 degree. So that means it is sort of, obviously this is not going to be exactly parallel to minus 180 degree axis, but it would go somewhere like this. So it would sort of be parallel to this minus 180 degree axis and it will follow a path like this. And the direction will be, it will start from omega equals to 0 and it will move like this and it will end somewhere over here. This is how you plot the whenever you are given with a polar or with a given transfer function. In case you have to find out or you have to draw what is the polar plot, so you have to proceed in this way. Okay. And similarly from the polar plot, what you can do is that you can find out what all will be the values of this gain margin and phase margin. So gain margin is, you have to find out what is the value of the gain crossover frequency, the phase crossover frequencies, and at those corresponding values, what is the real component, what is the imaginary component. So once you can identify those frequencies and the corresponding values of the magnitude and phase, you can find out or you can comment on the relative stability of the system. So if both the gain margin and the phase margin, they are positive, then we say that the system is stable. If one of them are negative, then we say that the system is marginally stable, or if both of, or rather if both of them are negative, we say that the system is stable. So in order, and depending on the value of this gain margin and phase margin, you can comment on the stability of the system. Okay, so similarly, if you have, let's say that you have another example where you have to find out, or you have to draw this Bode plot of this transfer function, and from there you have to determine the gain margin and the phase margin. Okay, so first of all, what we do is that we have to draw the Bode plot for this one. Okay, so the first step would be to draw an approximate Bode plot. Okay, so if this is GH is given by 20 by S into S plus 2 into S plus 10. So that means you can write in terms of J omega. So this would be 20 by J omega into 1 plus J omega by 2, 1 plus J omega by 10 divided by 20. So this 20 gets cancelled out. So you have 1 by J omega, 1 plus J omega by 2, 1 plus J omega by 10. So here you have 3 poles of this system. So one is at the origin, so that means it would be a minus 20 dB per decade straight line. Okay, so it would be a minus 20 dB per decade straight line. Then once you encounter, so this is your first corner frequency corresponding to this one, and this would be your second corner frequency. So let's say the second corner frequency is here. So that means that from here there would be, so this is a minus 20 dB per decade straight line. Okay, then at this point, since there is a first order pole over here, so that means another minus 20 dB per decade straight line will come. So now this overall, this becomes minus 40 dB per decade, right? And at omega equals to 10, again you have a first order pole, so that means another minus 20 dB per decade will be added. So this would become minus 60 dB per decade. Okay, so this is your omega and this is your magnitude in dB, right? So but this is an approximate plot. So what you have to do is that you have to find out the actual plot, because since you need to determine the gain margin and phase margin, so you have to find out what is the actual from these plots. So this is a rough plot, you can say. So from here what you need to do is that, so you have to form a table. Okay, so in that table you will have, so let's say you have to form a table. So in this table you will have different values. So you take different values of omega. So let's say you start from, so let's say you start from 0.1 to some point in between. So let's say you have 0.1, then you have 0.5, then you have 1, 2, and in between, let's say you have 5, 10. So take different values, and for those different values you have to find out the magnitude of the, or the gain in dB and the phase angle, right? So once you have found out corresponding to each frequency this gain and phase angle, so you can simply plot those points and you can draw a smooth curve, and that would give you the and remember here, since you have to find both the gain margin and the phase margin, so what you have to do is that you have to plot both the gain magnitude or the log magnitude plot as well as the phase plot. Okay, so once you have drawn the phase magnitude, phase and the, so let's say the plot looks something like this. So this is, okay, so this is omega. So here you have dB, and here you have the angle in degree. Okay, so here let us say that you have, your plot looks something like this. Okay, and it is, so this is your 0 dB line, and the phase plot is also, will also look, let's say it looks something like this. Okay, so this is obviously not the actual plot. You have to find out from the table the actual how it would look like. Okay, so this is just a rough plot. So you can say that this is, let's say this is minus 10, then you have 10, then let's say this is 20, and so on and so forth. And let us say that this starts at minus 100 degree, then you have 120, then you have 130, and let's say this is minus 180 degree, something like that. Okay, so in order to find out the gain margin and the phase margin, so you have to find out the gain crossover frequency. So the gain crossover frequency means that the frequency at which, so this gain crossover frequency will be the frequency at which this crosses the 0 dB line. So let us say that this frequency is omega g. This is the gain crossover frequency. Okay, and at this gain crossover frequency you have to find out what is the value of this phase angle. So this phase angle will be, let us say, some value. Okay, so from this plot actually you will see that the value of omega g is equals to 4, and this phase margin is basically defined as 180 degree minus the phase angle at the gain crossover frequency. So the phase margin would be this much. So this is the phase margin. So you can write that the phase margin, from the plot you can find out the phase margin will be equals to 78 degrees. And similarly, if you find out the frequency at which the phase plot is actually intersecting the minus 180 degree line, so this is nothing but your phase crossover frequency, right? So this is PC. So this is your phase crossover frequency, and at this phase crossover frequency, let us say that we have to find out what is the gain. Okay, so let's say the gain is somewhere over here. So from 0 dB, so this would be my gain margin, right? So the value of this gain margin is equals to 21.6 dB, right? So now what you have to do is that, so that means that you have a margin of 78 degrees. So that means that you can play around, or you can change the gain or of your system in such a way that even if the phase angle of the overall transfer function it changes by an angle of 78 degrees, still the system will be stable. Similarly for the gain, if the gain of the system it changes by 21.6 dB, till that point your system will be stable. Beyond these points, the stability of the system will reduce and it will go into instability. Okay, so now if you have to, so it is given that you have to find out that how much gain of the system you have to increase so that the gain margin becomes equals to. So now in the second part, the desired, let's say, gain margin is given as 6 dB. So that means the gain of the system previously the gain margin was 21.6 and the new gain margin is 6 dB. So that means the difference should be so the gain of the overall system should be increased by the difference. Okay, so the overall difference will be 21.6 minus 6 dB. So this is equals to 15.6 dB. And the gain corresponding to this, let us say if that is called the gain factor. Okay, so let's say the gain factor is A. So that means A will be 20 log of A will be equals to 15.6, and from here you can find out the value of A. So A will be equals to 6.03. So you have to increase the gain of your system by 6.03 in order to have a gain margin of 6 dB. Similarly, since it is given that the desired phase margin is now equals to 45 degree, right? Previously the gain margin was equals to 78 dB. So this gain margin also, for this phase margin also, we have to adjust the gain of the system, right? So for that, since the gain margin is 45, the phase margin is 45 degree. So what we have to do is that, so 45 degree, or you can say that this is equivalent to minus 135 degree, right? So from this plot, from this phase plot, you have to find out that what is the point at which what is the value of this omega at which the phase angle is 45 degree or phase angle is minus 135 degree. So if you see from the phase plot, you will find out the value of omega is equals to around 1.5 radian per second, at which the phase angle is equals to 45 degree, right? So, and at this omega equals to 1.5 radian per second, you can simply find out from the magnitude plot what is the value of this overall magnitude of the system. Okay, so you see, and that gain, so at this point the gain of the system can be found out from the log magnitude plot, and this is nothing but minus 5.5 dB, right? So that means that in order to have a phase angle or a phase margin of 45 degree, you have to increase the gain of the system by 5.5 dB. So that means that the overall gain of the system has to be increased by a factor of, similarly like here also. So log A dash will be equals to 5.5. So from here you can find out the value of A dash, which will be equals to 1.88. So depending on how much gain margin or the phase margin you want to have in your system, accordingly you have to change the overall gain of the open loop transfer function. Okay. So next we will move on to something which is known as which actually tells us about how to analyze stability in frequency domain. So we know that in time domain, if we want to analyze the stability of a system, what we do is that we use either we use the Routh-Hurwitz criteria, or we use the root locus method in order to find out, or in order to comment on the stability of a system, right? So the system stability, it depends on the location of the roots of the characteristic equation. So the roots of the characteristic equation, they are nothing but the poles of the closed loop system. So we can say that if the poles of the closed loop system, they lie on the imaginary axis or on the right half of the S-plane, so that means the system will be unstable. If they lie on the imaginary axis, they will have sustained oscillations, and if they are on the right hand side of the S-plane, they will have exponentially increasing oscillations, and it will ultimately lead to instability. So using this root locus method, what we can do is that we can determine the exact positions of the root of the closed loop poles, because in root locus what we were doing is that we were drawing the root locus for the open loop transfer function. So for the open loop transfer function, we were varying the value of the gain of the overall system, and we were monitoring what will be the corresponding position of the closed loop poles. So depending on the root locus, we can determine, using this root locus technique, we can determine what all are the positions of the roots of the characteristic equation, or in other terms, what are the position of the poles of the closed loop system from our open loop pole zero configuration. Okay, so this was about the time domain criteria. Okay, but in case of frequency domain, when we are talking about, or when we are analyzing the system in frequency domain, so what we use is that there is something which is known as Nyquist stability criteria. Okay, so what this Nyquist stability criteria it does is that it relates the location of the roots of the characteristic equation. That means it relates the position of the closed loop poles to the open loop frequency response. So in this case, the best part is that we don't need to compute separately the closed loop where the closed loop poles of the system will lie. Okay, so if you plot the frequency response of a given system, if you plot this Nyquist plot, just by simply studying the Nyquist plot, you can say whether your system is going to be a stable system or not. We don't need to calculate all the different positions of the locations of the closed loop poles. So this is the best part about studying the stability in the frequency domain. Okay. So before going into the Nyquist stability criteria, first let us talk about a few mathematical background which actually leads to this Nyquist stability criteria. Okay, so now let's say that we are considering a polynomial. So let's say we are considering a function QS. Okay, so QS is basically a ratio of two polynomials. So these are the two polynomials, right? So now if you substitute the value, so S is obviously equals to sigma plus j omega, right? So that means if you substitute the value of S with sigma plus j omega, so then what you will end up again, so this QS will also be a complex quantity, right? S is a complex quantity. So that means if you substitute S with this complex number and then you do rationalization and all, so then you will find that QS is obviously going to be another complex quantity, right? So let us say that we describe QS is equals to U plus JV, okay? And we will be plotting the value of QS in the complex QS plane. So wherein the x-axis will be U and the y-axis will be V. And in case of the S plane, so corresponding value of S will be, in the x-axis will have sigma and in the y-axis will have omega. So we can say that for every point S in the S plane, so let's say that we consider any value of S. Okay, so any point S, let's say we consider a value of S1. So for this corresponding value of S1, if you substitute this value in QS, obviously you will get a value of QS will be in terms of, let's say, U1 plus JV1. Okay, so let us say that corresponding value is over here, right? So S1, the value of S1 in the S plane, that sort of, so you can say that it maps on to the QS plane as a value, let's say QS1, right? Similarly, you can have other different values of S for different values of S in the S plane. You will have a single corresponding mapping or a single corresponding value in the QS plane. Okay, and this mapping will be valid in case this QS, this is an analytic function. So analytic function means this function and all of the derivatives of this function, if that exists, if the function as well as all of its derivative they exist, in that case the function is known as an analytic function. Okay, so if QS is an analytic function, then for each value of S1 in the S plane, we will have a single or a corresponding point in the QS plane. So alternatively, you can say that this QS plane, so QS basically maps points on the S plane into the QS plane. Okay, so this would be a sort of one-to-one mapping. Now, since any number of points can be mapped onto any number of points in the S plane, they can be mapped onto the QS plane. So you can say that if we draw a closed, let's say a closed contour. Okay, so this, let's say we start from S1, we draw contour like this in a clockwise direction. So that means this, and we calculate what would be the value of QS for every point on this contour, right? So that means that for this contour, there will be a corresponding contour in the QS plane also, right? And so this basically, so since any number of points in the S plane can be mapped into the QS plane, so you can say that the contour in the S plane, which does not go through any singular point means the point at which the function as well as its derivative do not exist. So that means the poles and the zeros of this function QS. If this contour does not pass through any of these poles and zeros, so in that case you will find a corresponding contour in the QS plane. So now if the region to the right of a closed contour that is considered, so see, so if since we are moving in the clockwise direction, so the right hand side, so if we are observing the direction at which we are going, so the right hand side of that part is said to be enclosed by this contour. So that means since we are considering, if we are considering this direction, so that means the right hand side will be like this. For this part, the direction is in the opposite way. So the right hand side of this arrow is this part. So all the points in this part is called enclosed by this specific contour. Okay, so you can say that the region to the right of the closed contour, that is considered as enclosed, or it is called enclosed by the contour when the contour is traversed in the clockwise direction. Okay. Now obviously, for this contour, there would be some contour in the QS plane also. But we are actually not interested in what will be the exact shape of this QS plane contour. Rather, we are interested in the number of encirclements, or how many times this QS plane contour that is encircling the origin. So this is the origin. So we are more, instead of being interested as to what would be the exact shape of this contour, we are mostly interested into how many encirclements or how many times this closed contour is actually encircling this, or it is going up around about the origin. So that is our point of interest. So the encirclement of the origin by the QS plane contour, that is important. So now let's say that in the S plane, so let us consider an S plane contour which encloses only one zero of QS. Okay, so QS is given by this. So the zeros of QS are given. So the zeros of QS, they lie at alpha 1, alpha 2 till alpha m, and the poles, they lie at beta 1, beta 2 till beta n, right? So let's say that we have, and we can plot, obviously in the S plane we can plot what all are the positions of these poles and zeros. So now let us consider that only we select a contour in the S plane in such a way that only one of the zeros of this QS that is enclosed by this contour. So in that case, and all the other poles and zeros, they are located outside of this contour. Okay, so that means that for any non-singular point S in the S plane, that there obviously there would be a corresponding point QS in the QS plane contour, right? So you can find out the magnitude of QS will be simply the product of magnitudes of each term divided by the product of magnitude in the each term in the denominator, and the phase angle would be equals to the angle contribution for each term in the numerator minus the angle contribution for the each term in the denominator. Okay, so now let's say that let's say that this is a pole. So QS is given in such a way, so you have one pole at alpha 1, there is another pole at alpha 2, 1 0 at alpha 1, 1 0 at alpha 2, and there are, like, let's say there are 1 2 3 poles. Okay, and we select a contour. So this is my contour in such a way that only this S equals to alpha 1, the pole at, or the 0 at alpha 1, that is enclosed by this contour, and all the other poles and zeros, they lie outside the contour. Okay, so if we now, let us say that we draw a vector. So we consider a point S such that we draw a vector from this S1. So this vector will be S minus alpha 1. Okay, and we change the value of S. That means the tip of this vector is actually following this contour. Okay, so it is starting from here, it is following the contour like this, and then coming and ending over here. Okay, and this is done in the clockwise direction. Okay, so it is moving in the clockwise direction. So you can see that since it is starting from this position, so as this is moving, so that means the phase contribution, it is getting added up. So all the phases due to different positions of S, that would get added up, and once it is ending over here, so that means this tip is starting, let's say this tip is starting from here, it is moving all the way somewhere over here and then ending over here. So you can say that it is actually covering one complete revolution. Okay, so that means the net angle which is encountered, or the net angle which is completed in one revolution, that is going to be minus 2 pi, right? Since we are moving in the clockwise direction. If we were moving in the anti-clockwise direction, we would have a net angle contribution of 2 pi, right? So here you can say that as the point S, it follows the prescribed path or this prescribed contour in clockwise direction. So, and it starts from this point, it traverses all the way, and eventually it moves to this point. So at this point, so let's say that this is, so let's say the contour is something like this. Okay, so that means this, the phasors are actually moving like this, and then finally it is coming back here. So that means it started from here, it moved all the way, and it ended here. So that means the net angle is equals to minus 2 pi, since we are moving in the clockwise direction. And similarly, so this is about the 0 which is enclosed in the contour. Now what about the other poles and zeros which are present, which are not enclosed by the contour? Okay, so for those things, what is happening is that similarly, if we draw different vectors from these poles and zeros to this point S, and so for these things, what is happening is that these vector, they are actually moving up. So while moving up, it is the angle contribution, let's say, is positive, and for every point here, since this is actually not completing one revolution, so this is basically either, so this vector is either moving up or it is moving down. So this is going, the direction of motion is either up or down. So that means it is not completing one full revolution. For every positive angle, there is a corresponding negative angle at a different point. So that means we can say that the overall phase contribution for the other poles, which are poles and the zeros, which are not enclosed within this contour, that contribution is equals to 0, or that generates a net angle of 0. So similarly, you can say, so this is about the S plane. So now if we talk about the QS plane, so in QS plane also, so this vector that would traverse a path, so this would be in a clockwise direction. Okay, so similarly we will get, there would be a contour in the QS plane, and the tip of the QS phasor, that basically describes the closed contour about the origin, and we are moving in the clockwise direction. So corresponding to this contour in the S plane, we'll get a contour in the QS plane also. Okay, and the net phase, the QS plane also, this is also, since this phasor, so this is the phasor, basically QS phasor, this is also moving like this, and it starts from here, it moves all the way here and comes back to this original point. So that means it is encountering a phase angle of -2 pi. So here also in the S plane as well as in the QS plane, the net angle or the net phase change is 2 pi in both the cases. Since the net change is -2 pi, since in both the cases we are talking, we are moving in the clockwise direction. And now in case there is no, so if a contour, let's say it doesn't, we choose a contour in such a way that it does not enclose any pole or zero in the system. Okay, so if it doesn't enclose any pole or the zero, so that means that the corresponding QS plane, that will also, so we will get a contour, but that contour will not encircle any origin. Okay, so similarly, if it encloses, like let's say 2 zeros, so enclosing 2 zeros of this one means that there will be two encirclements of the origin. So the origin will be encircled 2 times in the clockwise direction in the QS plane. So it will, let's say it starts from somewhere from here, it goes like this. So this is one encirclement, it moves on like this. So this is encirclement number 2. So you see that this origin is basically encircled 2 times by the QS plane contour. So as in order to generalize, you can say that for each and every zero which is zero of QS which is enclosed by the S plane contour, the corresponding QS plane contour, it encircles the origin once in the clockwise direction. So if you have one zero of QS encircled by the enclosed by this QS plane by this S plane contour, that implies that the QS plane contour will encircle the origin once in the clockwise direction. If you have two zeros enclosed by this S plane contour, that means that there will be the encirclement of this origin in the QS plane contour will be 2 times. So this was about the about some contours which are enclosed by or the zeros of the function QS that is enclosed by the S plane contour. Now what would happen if instead of enclosing the zeros, we enclose some poles? Okay, so now let's say that if you, in case of enclosure of poles, that means that we have S minus beta 1. Okay, so let us say that we have, in case of S minus beta 1, so what we'll have is that this S minus beta 1 obviously will, so here similarly in this case, instead of this 0, we'll simply have a pole. So in case of a pole also, this phasor, so let's say if this pole is beta 1, so that means this phasor S minus beta 1, that would encircle or that would encounter a net phase angle change of -2 pi, right? But in this case, what is happening is that the moment we are moving or we are mapping this contour into the QS plane, so since this S minus beta 1, this is present in the denominator. Since this is a pole, so that means it is present in the denominator. So that means the phase angle contribution in the QS plane contour, that would experience a change in net angle of +2 pi. So that means it would, for each pole of QS which is enclosed by a S plane contour, the phase angle which is, so if you have, let's say, if you enclose, let's say, a pole over here, so this is, let's say, minus beta 1. Okay, so this is your S plane, sigma j1, right? And we are moving in the clockwise direction. Okay, so similarly, if you enclose a pole, so in this QS plane, you will have, so this origin that would be enclosed by, it would be enclosed like this, but it would experience a net phase angle change of +2 pi. So that means it would be encircled in a counterclockwise direction. So that means it will, so if you have, this is the, so let's say this is your vector. So this is your S minus beta 1 vector, and similarly this is your QS vector. So this QS vector will now experience a phase angle of +2 pi in the QS plane, since S minus beta 1 that is present in the denominator. So that is why the phase angle will become 2 pi. So you can, in general, you can say that if, let us say that if p number of poles and z number of zeros of this function qs that is enclosed by this s-plane contour, so that means that the corresponding qs plane contour also it will encircle the origin. So z times, so z0, z times in the clockwise direction and p times in the anti-clockwise direction. So that means the net encirclement will be equals to p minus z in anti-clockwise direction. Or if the value of p is less than z, so that means it would be z minus p times in clockwise direction. So depending on how many poles and zeros are enclosed by a contour in the S-plane, depending on that, the number of encirclements of origin in the QS plane that is determined. Okay. So similarly here, let's say that we have 3 poles and 1 zero. So 3 poles and 1 zero is encountered or is enclosed by this S-plane contour. So that means in the QS plane, what will happen is that, so you have you have 1 pole means you have 1 clockwise encirclement, and you have 3 poles, so 3 anti-clockwise encirclement, right? So overall you can say, so 3 minus 1, 2 encirclements of origin in anti-clockwise direction. Okay, so that means that the overall angle which is experienced, that is equals to 2 pi multiplied by 3 minus 1, which is equals to 4 pi radian. Okay, that is same as 2 counterclockwise revolutions. Now this relation between enclosure of any number of poles and zeros by the S-plane contour and the corresponding encirclements of the origin in the QS plane, this is basically, this relation is known as the principle of argument. Now based on this, what we'll do is that we'll try to derive what is the Nyquist stability criteria. Okay, so now let's say that, so let us say that now QS, which was a polynomial in the previous case, let's say that QS we consider as the characteristic equation of a single loop feedback system. Okay, so a single loop feedback system means, let's say that you have just G over here, you have H in the feedback. So this is just a simple control loop you have. Okay, so minus plus, this is your output, this is your input. So that means the overall transfer function of, or the characteristic equation of this system will be QS is equals to 1 plus GSHS is equals to 0, right? And now let's say this, the value of GSHS that is given in this form. So in pole 0 form it is given that M, the number of the order of the numerator is less than or equal to the order of the denominator, right? So simply you can write QS will be equals to 1 plus this term. Okay, so 1 plus this would be, if you simplify, in the denominator you have S plus P1, S plus P2 till S plus Pn, and in the numerator you have S plus P1 plus S plus P2 till S plus Pn plus K into S plus Z1, S plus Z2 till S plus Zn. Okay, now since the value of this this denominator, or the order of the denominator, is higher than the order of the numerator, so you can say that if, irrespective of what is the value of this M, so the order of this numerator term, this S plus P1, S plus P2 till S plus Pn, and this numerator, the order of this one should, so order of this numerator should be equal, always equals to n, because let's say that you have a transfer function where it is given by k into s plus 2, and in the denominator you have s square plus 3s plus 1. Okay, so here m is equals to 1 and n is equals to 2, right? Now if you write the corresponding characteristic equation, so it would be 1 plus k into s plus 2 by s square plus 3s plus 1 equals to 0, or in the other terms you can write s square plus 3s plus 1 plus k into s plus 2 equals to 0. So here also you see that the order of this numerator of this term, that is equals to the order of the denominator, since in this case we are considering that for physically realizable system, always the order of the denominator polynomial that is greater than the order of the numerator polynomial. So that means both the, so now if you can simply sort of simplify or factorize this numerator term. So you will, let's say that you end up with values at, so the factors are s plus z1 bar, s plus z2 bar till s plus zn bar. Now the order of both the numerator and numerator and the denominator are n. Okay, so you will have n number of poles and n number of zeros of this characteristic equation Qs. Or in other terms, you can say that the poles, the zeros of this Qs, they lie at this point minus z1 bar, minus z2 bar, minus zn bar. In other terms, you can say the roots of the characteristic equation, or in other terms, you can say that these are the poles of the closed loop transfer function on the closed loop system. And if you observe the poles of this QS, so poles of this QS are nothing but the poles of the given of the open loop transfer function. See here the poles of the open loop transfer function. The denominator polynomial real remains the same for both GSHs as well as QS. So you can say the poles of QS, they lie at minus P1 minus P2 till P minus Pn, and they are same as the open loop poles. So from this characteristic equation, you can find out what would be the roots of the characteristic equation as well, or rather you can have information about what would be where the poles of the closed loop system will be located and where the poles of the open loop system are located. Now, in order to have a stable system, what we need is that the roots of the characteristic equation, they should all lie in the left half of the S-plane, right? So the roots of the characteristic equation, that means the roots of the characteristic equation are nothing but the zeros of QS. So for a system to be stable, the roots of the characteristic equation, or rather the zeros of QS, they must lie in the left half of the S-plane. Now you note here one more thing, that is that you might have a system where some of the open loop poles, they lie on the right half of the S-plane. So if some of the open loop poles, they lie on the right half of the S-plane, so that means that the open loop system is going to be unstable. Okay, so in that case also, depending on the feedback mechanism which you have, so it might so happen that all the zeros of this QS, so zeros of QS means the poles of the closed loop system, they might lie for the even though some of the open loop poles, they are on the right half of the S-plane, that is, even though the open loop system is unstable, you can still have the closed loop poles lying on the left half of the S-plane. So that means that all the zeros of QS, they will lie on the left half of the S-plane. So you can make an unstable open loop system, you can convert it into a stable closed loop system, which is one of the reasons which we studied back in the first class, that why the advantages of using a negative feedback. Why we want to use a negative feedback is that we want to improve the stability of the system. So an unstable open loop system can be converted into a stable closed loop system, even if the open loop system using a proper feedback mechanism. Okay, so I'll stop here today. Do you have any doubts? Class tomorrow at 11 o'clock. Thank you, everyone.